Okay, this part will be slightly different. It's about determining probability of detection through nonlinear modeling, and I will try to explain during the introduction why we find it useful. This part was prepared together with my colleagues. Živa Ramšak prepared the R command lines that we are using. Aleksander Benčič did the video demonstration that you will see. And Špilalić did a lot of work on the data that you will see on the validations that gave rise to this analysis as well. So without further ado, again, question from the application: how familiar are you with R statistical? Here a bit fewer people are planned to participate in this part. And many said that you are not familiar with it at all. And some of you said that, a quarter of you said that you use it for basic visualization and data manipulations. So it seems that none of us is really an expert user or writing their own scripts. And I can say that I am here under using it for basic visualization and data manipulation, and that's being slightly optimistic. Is that the right word? I don't use it constantly. I use it when I have to prepare a certain figure. Sorry, just have to put my time. So do not worry, this part will not require you to become a statistician or turn into an expert user in R statistical. We will try to equip you with some of the things that may be useful to you. So remember from the previous lecture, sometimes we have tests that perform very similarly. So based on this data, it's quite difficult to really select which one we are going to use based on evidence on analytical sensitivity, for example. And finally, when we have to move the standard curves and the results left to right, because we determine the concentrations and we realize that, for example, this 10 to the 4 is not really 10 to the 4, but it's 5 times 10 to the 4, but this one may be 3 times 10 to the 3. We would like to shift these standard curves and compare them in a more meaningful way. So, but the problem with the approach that was presented before is that we only know what is happening at the actual tested concentration. So what we want to do is to extend from that data to the concentrations that we were not testing but are still interested in. So for example, in this area here, what is happening here? And to do this, we can use nonlinear modeling. And this is a way of describing relationships between target concentration and probability of detection. And probability of detection is nothing else than the number of positive reactions out of all reactions at each concentration. So we basically, for example, take 3 standard curves. Here it is shown for real-time PCR, but it can be any test. And for the different concentrations that we have prepared, we count the number of positive reactions. For example, here for standard curve 1, 3 out of 3. But then with lower concentration of the target, of course, we come to concentrations where this number decreases. So here at 10 to the 3, it's just 1 positive out of all reaction and the same in 1 concentration below. So taking all this data together for all 3 standard curves, it basically gives us 100% positive reactions at 10 to the 6, 100% positive reactions 10 to the 5 and 10 to the 4, but then it slowly decreases. And we can use this data by plotting them on such a plot where on the X we put logarithmic concentration in, for example, cells per mil. And on the y-axis, we put probability of detection, this 100% or 87% or 20%, etc. So basically what we know and what is usually, if our test is any good, what we usually see that at higher concentrations, we get 100% detection. So everything is positive. With lower concentrations, everything is negative. The interesting things happen in between. So around theoretical LOD of a test, typically for molecular methods between 10 to the 4, 10 to the 3, where we can analyze the actual experimental data, and we get, for example, this sort of probability of detection. So this number of positive out of all reactions that we are testing. So basically what you can see that we could really draw a nice curve through these points. And this is basically what we are doing with nonlinear modeling. We cannot draw a linear straight line, but we can do nonlinear modeling, fitting this sort of curves to the points that we have. And through that, we can then see that different tests have different number of positive samples, which correspond the expected number of positive samples, which correspond to the area under the curve. Some of you may be familiar with this from assessing bioassays or pathogenicity tests. And on the other hand, we can basically correlate different probability of detection with concentrations and vice versa. So we can basically take this and read out what is the probability of detection at 10 to the 4, but also 5 times 10 to the 3 that we did not test, or slightly above 3, we can go like this, and we see, okay, at this concentration, we have this probability of detection. So we are basically filling in all the missing spaces between our experimental data. What we often do is to introduce additional experimental points, so additional points in our standard curves, typically points with final concentrations between 10 to the 4 and 10 to the 5 and 10 to the 3 to 10 to the 4. So this idea behind this is that here in this area where there are lots of things happening and things can go a bit higher or a bit lower, we have a bit more points to make the modeling more reliable. A few examples. This is an example of a real-time PCR AMSC assay and the influence of DNA extraction. So we analyze the same standard curves using 3 different DNA extractions, and we have compared them through nonlinear modeling. So we can see, for example, that with the simple DNA, we get a decrease in probability of detection at higher concentrations, but here it then just lags on, and we still get some detection later on. So here then we have a bit of more information how our test behaves, and then we can decide what is more important to us. Is it more important to detect this part but lose this part, or we want, for example, in this case, BioNobel quick pick DNA extraction because it provides the more repeatable lower concentration detection, but peters out earlier on, for example. Another example is transferring of assay, for example, from 7900 SDS instrument at the time to Smart Cycler, which is depicted by dotted lines. And some of you may be familiar with Smart Cycler. It enables higher volumes of sample to be analyzed. The reaction anyway is typically 25 microliters, but also the reagents that are used can be even lyophilized, and that means that basically you can resuspend the lyophilized reagents in your sample, thus using really high volume of samples. And that can, of course, improve analytical sensitivity of a test. Again, what you put in can be detected. What you don't put in cannot be detected. Okay, this is another example of optimization of a test for low-level detection. This is again an example of Erwinia Milovera. This work was done at Agroscope in Switzerland together with Dr. Braun-Kuning, Andrea, and with Brian Duffy. And we were trying to detect Erwinia amylovora in apple blossoms, asymptomatic apple blossoms, with the aim to predict infection or to add additional information to the prognostic models. And we were comparing different tests. These are serological tests, LFD, agri-strip tests. This is the real-time PCR that we started with, and we tried then to optimize it for low-level detection. And basically, this is what we got with that optimization. And this optimization included some concentration steps and, again, increasing the sample volume. So you can see that it basically provides also a bit more visual information on the comparative performance of tests than just tables. So this nonlinear modeling, of course, we can draw this sort of lines through the points, but that isn't really helpful, or at least is not that accurate. So we need some tools that will help us with that. And what we are using is our statistical. As I wrote in the introduction to the lecture, which was in the program, there are, of course, professional programs that do the same thing. Of course, there are many programs that can do nonlinear modeling, but this one is a free software environment, and we find it useful. So we thought that we will try to share our experience with that. So our statistical is basically a programming language and a free software environment for statistical computing and graphics. It's freely available from this web page. You can install it. It's available both for Windows and other platforms. It's command line based, so basically you have to type in all the instructions, but it has graphical interfaces also available. For example, RStudio, which will also be used in the demonstration that you will see. So basically, what you have to do this work, you have to download core R. So this is like the basic R that is always there. And then after you have this, you are installing small bits of programming that you are interested in. And for this particular work, for nonlinear modeling, for this purpose, we are using DRC package, dose response curve package, that was described by Ritz et al. Already in 2015. You will also receive commands that you can either copy paste into R or execute in RStudio. There are, of course, a lot of tutorials available on YouTube about R statistical. This is one that I find useful. It's by this one at the bottom. It's by Hefin Riss. I'm sure I'm not pronouncing it correctly. But if anyone is interested into more deeper understanding of the R, this is a good introduction to start. But as I said, for this part, we hope to show you a way to do it without studying all the intricacies of R statistical. One of the obstacles that people usually encounter when they start working with R is simply getting data into R. There is a way that you need to read it, and that means that you need to prepare the data in the correct format. It has to be, we have in this case, TXT format. You have to have decimal points, not commas, for the basic reading at least. And the example that we will show and the file that you will get is this one. It has a long name in Slovene, but it's a real-time PCR data for detection of Ralstonia solanacearum species complex using real-time PCR based on Wheeler primers and Vryburg probes for detection of these bacteria in latently infected potato tubers. So samples of 200 tubers in combination with quick bionobal DNA extraction. And the data is structured, basically this is repeat, so standard curve, log concentration, that is the concentration of bacteria per mil, and the probability of detection. So 1 is 100, 0 is 0%, etc. Okay. We will go through the demonstration later, but just to show you how this, the commands look like. The things that you also need to do this job are installed right at the beginning. So by this, writing this or copying this into our command, our console, and this basically installs all required packages. The next one basically tells the program in which folder you have your data and where do you want to work. And here you can see this long name that is basically the path that was used in the video demonstration that you will see. And the path is the thing that you see when you are opening folders on your computer, and there's this address line, path line. The only thing that you have to do is copy that when you have your own data stored somewhere else. Of course, you will not have this exact name. You just copy it, and then you just have to change this slash for the other slash. Sorry, I don't know the English words. And then the next thing is to read the data. And here again, this is the file name together with the extension in this, inverted commas. And the whole command looks like this. So the things that are marked with asterisks are the things that you will change when you have your own data. So you will have a different file name and particularly different path name. These commands basically create folders in your working directory where the models will be generated in, as you will see, in PDF files. So the next part of this long list of commands you will get are basically descriptions. So anything in R statistical that starts with this, how's this called in English? I don't know, how's this sign? But these are really not commands. Hashtag, thank you. Thank you. These are basically not commands, they are just a description for you to understand, and basically to understand better what is going on, and are basically notes of that the one writing this command lines to later on comment, remember what they did. And these are the models that are included in this package, and that the package tries to fit to our experimental points.
Hello everyone, in this video I'm going to present you our R script for the calculation of probability of detection and limit to detection. Let's first check out our data we're going to use for this calculation. The data have to be saved in a text file like this one, and it includes the decadic logarithm of concentration and the proportion of positive samples. Now let's open the R script. So to run this R script, you need these three packages here, and if you don't have them installed yet, you must do it before you run the script. Okay. So first we set the working directory to where we have saved our data before, and I already did this for my data, and now we can import our data from text file into R. And it's simplest way is to copy paste the name of the file into R and run the code. And then we create the directory in which we are going to save our data from the calculation, just like that, and then we set working directory to the newly created directory. So this R script calculates the probability of detection at different logarithmic concentrations, and also calculates confidence interval, and it plots the result of this calculation on a chart. For the calculation, it uses a few different models which are listed here, and this script basically uses all of these models for its calculation and calculates separate results for each model. So now let's run our script. Okay. Now run script, and now we can check the results. The results are saved in this folder we previously created and are saved in this PDF file. And here we can check the results of calculations for all models and compare them to one another. Then the script also analyzes these different models and chooses the best model and saves it in a separate file based on the lowest relative standard error. And the results of this analysis are also saved in a separate text file, which is this one here. And the best model is saved in this file. I'm going to open now. For the best model, script also calculates limit of detection with the concentration of the probability of detection of 95%. As you can see here on this graph. So this is how our script works, and thank you for your attention.
Basically, I have opened my RStudio, which is the graphical interface. If you will be only using let's say naked R statistical, this is the part you will see. You will not see any of this part. And if you're working with naked R statistical, you will basically just copy things from the file, TXT file with all the command lines into this part. But if you have RStudio, you just go and open file and you search where you have your commands. And this is the file where all the commands that I have been showing in the presentation and that were used in the video are listed. So I will just open them and I see them now here. So this is basically what all that we were looking during the presentation with this large part that was not in the presentation that is just executed in the end. So basically here you can see that I have the same address as was in the video demonstration. But at this stage, so I want to change this. I want to go into a different folder to do this. Just I will just have to close a few things. Okay. So for example, I want to, let's say I want to go here. This is where I have my data. So this is my data file. So basically I can just go here and I just copy it, but then I have to, yes, there was a question. Yes, all presentations will be available together with the recordings, and you will receive all this data as well. So the command lines, etc. So I have to change this. And the file name in my case is the same, so I will just leave it as is. So just to be sure, okay, I have to, so if I'm in RStudio, I just go here and I put Control Enter, and it transfers, sorry, I'm showing you on the screen, it transfers the command where I'm at into this part and does something, whatever it needs to do. So here I have just told the program to install the libraries that I need. If I didn't have them, they would get installed. Otherwise, they just get loaded if I haven't loaded them before. So I go to the next point. It's basically reading the data file. Again, in RStudio, Control Enter. So you see that it transferred it here and did something. And then if you are a novice, it's probably the easiest. If you just take all this bit, just copy it, go here, just click Enter, and everything should be done. So takes a bit. But here we have this pests2 folder, where all the data of the modeling is generated. So we have the same thing that you saw in video demonstration. All the different models, these are descriptions of the different models. We were really unlucky with choosing the data. It's not the best to show how different models fit, sorry about that. But you have, for each of the models, you have a graphical representation, and some are better than others. Where there is a bit more residual error, you can see, for example, here, that is designated with this shaded areas. So this means that there is less fitting of the model. The fit of the model is not as good to the experimental points. So this is the first thing that we get, all the models. Then we have this sort of data for different models. This last number is the residual error. So the higher the residual error, the worse the fit. So you want a model that has low residual error. Basically, you are deciding what is the best model mainly on the residual error, and just looking at it, seeing whether it fits or not. But this script already proposes you what is the best model. Sometimes it's worth checking because it's not always actually the best one. It might have the lowest residual error, but visually you can see, okay, I should probably go with a different one. So it's always worth checking in the previous one. And for the best model, it basically does what we were describing in the presentation. So it takes 95% probability of detection and checks at what concentration that happens. And in this case, it's log concentration 3.361. So it's this concentration cells per mil. This is the LOD of 95%. Okay. Was it, were you able to follow this explanation and see it maybe a bit clearer? Can anyone hear me? I don't hear.
It was clear. In the chat, we received 2 answers that it was clear, so just proceed.
Okay, 2 out of 60. We are doing fine. Okay. Okay, so I will just go to the next slide. And you will receive with this in connection to this presentation, a recording of the presentation, a PDF of all slides, this R script, the list of all comments in TXT file, and the sample data that was used in the demonstration together with the files generated in the demonstration. So the PDF files and the TXT files. And the separate, we will include the link to the video on YouTube. So this video demonstration, and this should be enough to get you started. So to try to test it and see whether it works. But please, if you encounter any difficulties, feel free to contact us and we will do our best. We are also not expert in R statistical, but we can try and help. Maybe to conclude this part, of course, we are aware that the number of points for each concentrations that we have is rather small. So for example, we typically deal with 3 biological repeats, 3 tubes, or 3 standard curves at each concentration level, and each is analyzed typically in real-time PCR in 3 technical repeats. So we have basically 9 data points per each concentration level, which of course, from the perspective of some statistical support, is not huge. But if you look back at the examples that we have shown, the effects of some modifications that we were introducing are quite high. So it still seems relatively clear that we are moving in the right direction. If we want to improve detection at low levels, we can actually see it in this way. And of course, this also means that we can all try to report not the same number, but a similar, looking at the same point. For example, deciding, okay, I will report for my test the LOD at 95% probability of detection, and I will report the concentration at which this happens. And going back, this will probably not be a concentration straight 10 to the 5, but it might be, I don't know, 7.056 times 10 to the 3. And this is something that we would not be able to determine experimentally. We have to go in between the experimental points that we have. Okay. So this is what I would like to conclude, that this nonlinear modeling allows us a bit more accurate comparison of data from different sources and coming together with different, sometimes even units, and especially not really comparing 10 to the 6 with 10 to the 6, being aware that none of them are really 10 to the 6, but something else, but compensating for that, and can reveal more intricate differences among tests than looking at the tables, for example, that we looked at in the first part. And yeah, it allows for checking and comparison of concentrations not covered by experimental data. So that would be all in this part. So thank you very much for your attention. I hope it was clear, and hope you will try it out and find it useful.